So just an introduction of Summit. Of course, everybody's aware of this, but officially was launched June 8th in 2018. We have received delivery of it starting actually the October before that in the cabinets and then the processor boards. Currently, the world's fastest system at 200 peak speed of 200 petaflops, and our last reported number was 122.3 petaflops on the HPL benchmark in June for the top 500 number. Also, it reached these other achievements: Green 500, level 3 system, number 1 system, and also top on the HPCG benchmark. It was used by 5 out of the 6 Gordon Bell finalist teams this year, as well as some other Gordon Bell applicants, and achieved the world's first exaopt calculation at 2.36 exaops and a mixed precision 1632-bit computation. It has not yet been officially accepted, but even though it has not been officially accepted, it's already been used for quite a few different science activities so far, which I'll discuss. Basically the architecture of the system. Main core component is the node, which contains 2 Power9 processors, and each attached to 3 NVIDIA Volta GPUs, and these are arranged in 256 compute racks, 4,608 compute nodes, and with a Mellanox fat-free interconnect. It's just another slide to show the architecture. I'll talk a little bit more, a little bit later in the talk about the node architecture here and how that's impactful for applications. Okay, early users. We were able to start using 1,080 compute nodes out of the final 4608 nodes back in December, and we started deploying users to that fraction of the system. We've had 13 CAR teams. CAR stands for the Center for Accelerated Application Readiness, and it's our organized activity to bring applications forward to get them ready for the next generation system. We had a CAR effort for Titan before this. It started in 2009, 2010, and now we've had this for several years. Here you see a list of the different applications here. Cherk Stratsma has head up this effort. These are in different science domains, and you can see the different PIs there. So those were like the top priority users for the 1,080 nodes of the system. Also, we've had other interests. We had a call for letters of intent and then for proposals for people for the early science program to be able to use Summit basically immediately after the system is accepted. And so we had a lot of interest there, and these teams were allowed to get onto Summit also and start writing their applications. Also, as I mentioned, they're Gordon Bell teams, and also, last but not least, the system acceptance test team, that people actually are doing the testing of the system prior to finally accepting the system and delivering it to the users. So just a word about the early science applicants. As I mentioned, 65 letters of intent and to request to use the system, and these will be the first users to get onto Summit after it's accepted. And I think it's interesting to note that of these 65 letters of intent, there were 12 that had a significant machine learning component. And this is kind of a step function change regarding the past, that we're seeing, a number of projects come in even before we even accepted the system. They're showing interest in using Summit for machine learning and deep learning, and it's very exciting. And there's also been a lot of interest not only in the early science, but also for the Insight program, which starts January 1st. We will be announcing, I believe, Monday who the winners are of this, but I'll just say for now there's been a lot of interest in using Summit. And as mentioned earlier, there are 5 different Gordon Bell finalist teams using the system. And just to summarize those a bit, first one, I was involved in this project. The Comet team used the tensor cores actually for not a machine learning or deep learning applications, but for a data analytics application. We found a way to use the tensor cores for this. Also, there was Prabat's team at Lawrence Berkeley. Their team used machine learning to analyze simulation data from climate simulations, and they achieved 1.13 exaops peak performance and 0.999 exaops of sustained performance for their code. University of Tokyo is another team studying earthquakes, doing earthquake simulations, and they have a variety of interesting and novel methods in this work. Use of trans-precision arithmetic. They have a novel preconditioning technique based on, that's determined by machine learning methods, and a number of other innovations in this effort. Also at Oak Ridge, the Mendel code, this led up by Robert Patton, and they're using deep learning to train neural networks to do hyperparameter search and for electron microscopy data, and achieved 152 petaops. And also there's a Lattice QCD team out of Lawrence Berkeley, led out of Lawrence Berkeley, using, among other things, mixed precision multi-grid solver to solve those problems. And if you're interested, the SCA team, the two Gordon Bell finalist presentations are Wednesday late afternoon and Thursday late morning. So our first impressions of the system are that it's a very, very powerful system. Coming off of from running on Titan to running on Summit, it's kind of amazing to see the speed up in your code. Very strong GPUs, and another nice thing is that in a number of ways the GPUs are getting a higher fraction of peak performance compared to the K20X GPUs in Titan, and that's another pleasant experience. We're sort of getting more than what we expected, and that's a great experience. And also the features of the system that are new, for example, the tensor cores, and also the burst buffers and NVMe devices, which people are using. It was used for at least two of the Gordon Bell finalist teams, used that heavily, depended heavily on that. And so, you know, we're scientists, we see new hardware, how can we use it? And we're going out and trying to do that. And also the Mellanox fat tree network with adaptive routing, which gives us really amazing, nearly congestion-free communication between the nodes. We've already got some impressive results on a number of the apps, and I will have to say the system has been somewhat rough around the edges. Earlier on, our policy at the lab has always been, don't wait and give us a finished product in terms of the software. Give us something early so we can start trying things out and getting our codes ready with it. And so we get that, and they're beta versions, and they have issues. And so we report the problems, we report the bugs, and our vendors work on those, and things get better over time. And things have gotten much, much better in recent months. Yes?
I'm curious, are you talking about the Power 8 system when you make a statement about your system? Or are you talking about Power 9?
Well, actually just Power 9, basically.
Okay.
Yeah, so Power 9. We did have a Power 8 system, Summit Dev, that was very useful to us, but it's mainly about the system, the Summit system. So I wanted to give a little bit of information before I talk about some of the apps here. I wanted to give basically some performance data on performance of the Summit node and how this is performing for us. This is some data taken from a paper and a talk that will be given at SC18, and just want to take some highlights of this, some of the stuff that I worked on in terms of benchmarking of the node. And so some of the important things here are two Power 9 processors. They're connected by an X bus interconnect to each other. There's a connection to its memory. It says 135 here, but the actual peak is 170 for each Power 9 to its memory. And then there are these connections here to the 3 GPUs through NVLink 50 gigabytes per second unidirectional, 100 gigabytes per second bidirectional, and also each GPU has its on-package HBM memory, 900 gigabytes per second peak performance. So I just wanted to show a few benchmarks since when you're actually trying to optimize your codes, it's useful to know what are the, not only the peak values, but what are like the achievable values that could be achieved in an idealized case, which may be less than peak. First of all, for the CPU memory subsystem, some results with the stream benchmark. On this table here, it says table 3. It says here peak at the top. That's, peak is our single cabinet system that's identical to Summit. And also ran some benchmarks on Sierra just for comparison here. And these are the actual numbers in gigabytes per second for these benchmarks. The peak here is 340, and the actual that we're getting is anywhere between 268, 272 to 275. Across the top, these are different configurations. We have core isolation enabled in some cases, so that we have like one core set aside or 2 cores set aside per Power 9 to service different system tasks, to reduce jitter and that sort of thing. So basically, we're getting very good performance, 82% of peak for the memory subsystem performance on this. It is an idealized benchmark, so actual applications with a complex mix of memory accesses and compute may be less, but for these idealized results for an actual true benchmark, these are the results we're seeing, and it's interesting to see this compares very well to our previous systems in terms of memory subsystem performance. Titan had a peak was 51.2 gigabytes per second. We achieved 67%, and Jaguar PF 25.6, 12.8 for each of the 2 sockets, and we got 75%. So a very good performance here of the Power 9 accessing its memory. Also some benchmarks of the GPU HBM memory. Peak is 900 gigabytes per second. I think the actual number is like 898. And just the different stream benchmarks of the 4 benchmarks, getting 788 to 831 gigabytes per second, so 88 to 92% of peak. And this was kind of amazing. Also, one of my colleagues came to my office saying, you know, are you getting higher performance on your memory on the GPU than Titan? And I kind of showed him the numbers here and everything. And very exciting that NVIDIA made some innovations in the GPU to improve memory performance. And since so many of our codes are limited by memory bandwidth, this is very good for our applications.
Just a comment. I think that improvement has been made from Pascal to Volta. That's when it was really realized.
Mm-hmm.
Yeah, because you can see that difference in peak percentage from Pascal to Volta.
Mm-hmm. Yes.
Yeah.
And for NVLink performance, we're coming off of using the PCIe 2, which was slower on Titan, and now we have fast PCIe 2, a fast NVLink connection, not only from the Power 9s to the GPUs, but also between the GPUs, and we benchmarked that also. I didn't include this here, but basically we're getting for the unidirectional performance, peak is 50, and we're getting around 46, so 92%. And then for bidirectional, we're getting about 86% of peak performance. So very good performance. There is one issue. I think developers, we need to try to avoid going through the X bus, because this will actually slow performance quite a bit. And actually you can see it here in this graph here that this is one rank on the lower CPU socket accessing its own GPU, and this is going across the X bus to the other GPUs, and so these numbers are lower. And a few codes might have a compelling reason to want to go through the X bus for accessing GPUs, but I think in general we want to avoid it because of this. And finally, the InfiniBand interconnect, 25, going outside of the node to other nodes, 25 gigabytes per second is unidirectional peak and 50 for the bidirectional peak, and we're getting basically about 89% of theoretical peak here. Over here, this is the Intel MPI benchmark runs, and run up to message size of 4 million bytes, and you have to have fairly large message size as this to reach the asymptote or come close to the asymptote, but very good performance when you get out there to larger messages. Okay, next I'd like to talk about a couple of applications, a little bit more of a deep dive, two applications that I've been involved with, and give some detail on this. I didn't put it on the slide here, but there actually is a talk tomorrow at the WACPAD workshop at SC18. The talk right after the keynote is more detail on the porting experience for this application. It's a GTC. It's a code that is used to model fusion plasmas for fusion reactors. And it's a code written in Fortran 90, accelerated primarily with OpenACC, and some parts are written in CUDA. And also there is acceleration for the CPU-only parts of the code. And I should mention also there is an OpenMP version that is a different version that I don't think has yet been merged in, that's in use for the Xeon Phi processor. And here you have a little details about the project. So some of the experience porting this code, it came into the project in 2014 already with some OpenACC directives. This was done more extensively and more thoroughly to the code to improve its performance. So OpenACC is very important to our codes. We use OpenACC for one of the 6 Titan car applications. It was the S3D combustion code. It was pretty much largely rewritten to restructure the loops of the code, and used OpenACC for acceleration for Titan. And several car codes use OpenACC, though I do want to mention that there is growing interest in OpenMP4 offload. There is one code on Titan that is actually using OpenMP4 on Titan in a production mode. And so I think, though OpenACC has been very important to us, there's growing interest in OpenMP4 also. More about GTC here. There is one particular part of the code which actually finds all the particles during the simulation that need to be moved to another processor because of motion of the processor. So there's basically sort of a sorting process and collecting those and sending those. And that actually has custom CUDA code to get high performance. It's a complex operation. Also, another change made to the code was a Poisson field solve to compute the field at each step that is used to push the particles. And the original code had PETC linear solver with IOU0 and GMRes iterative solver. And we basically interfaced the NVIDIA AMGX multi-grid solver to GTC, and saw a huge improvement to performance. And also, there's a hyper multi-grid solver that's also been interfaced, and that's been getting some good results. That's in the process of developing GPU support. Another thing that is useful for our codes is unified memory, automatic migration of memory pages to the GPU, and we did some experiments with that and found out our initial port to use unified memory for some of the data migration was very slow, but we tracked this down to some compiler issues with the PGI compiler. Those were reported, and now we're getting near parity of performance using unified memory compared to explicit transfers.
So does unified memory allow you to get through the bottleneck of XBus?
No. That's pretty much a hard limit. If you want to go off socket to
Yeah,
another
exactly,
GPU.
because unified memory is useful if you have the NVLinks connections, not using the X bus, right?
Right.
So I was just wondering that did unified memory solve that problem of the X bus interconnect as well?
It doesn't really solve the performance problem. I think it will be useful to code some codes for just simplifying your code.
Right.
But in terms of getting performance out regarding the X bus, I don't think it will help too much.
Because if we intend to connect more such computing different architectures together, and if we have such a unified memory approach for them as well, so I was just wondering that would it be bottleneck or not? So I think thanks for answering that. So I get that idea.
Yeah. And even with unified memory, it should simplify coding for a lot of our users, but also the performance will need to be managed. There are like hints for controlling the migration. Maybe you want to start a migration of data earlier than what would be done automatically. So it requires some attention in some cases. And one other thing, GTC is also part of the acceptance test suite, and we were able to uncover some I/O behaviors that were a problem that with the GPS file system, and those were fixed as a result of those findings. And here's a weak scaling graph here, increasing the number of particles pushed as a function of the number of nodes, and getting very good performance weak scaling to sum it up to almost the whole system, over 4,500 nodes.
This is including GPU as well.
Yes. This
So
is.
5,000 GPU card.
Pardon me?
How many GPU cards?
How many? So 4,500 nodes times six GPUs per node. Yeah. Approaching 27,000.
Not including your personal software inside it.
Yeah, it includes the Poisson solve.
Is it MTX or is it?
AMGX.
May, this is maybe remotely related, but is Betsy library available on POWER?
It is. It doesn't use the GPUs, but it builds and runs fine on Power.
Okay. I think with this technology we have GPU built by single node, not one discrete student. So they also have a separate one, I think called NCL with OpenCLs, which is distributed. But and we also couple interface for AMGX as well. So you could potentially, there is a open source GitHub. We have a repo for testing using AMGX. So you can use that as well.
And I believe this application is high precision only. So the precision.
Actually, I think they can use it in single precision.
Single precision.
Yeah.
Okay, not mixed, right?
Right.
Okay.
Okay, second code I'd like to discuss is Comet. It's a newer code. It's a Biosciences application, combinatorial metrics code. It's not a traditional modeling and simulation code. A lot of us are familiar with PDE solvers to solve continuum problems, or particle pushing, Monte Carlo codes. So it's more of a data analytics code, and it's also not a deep learning code, but the output of this is fed into an AI workflow. There will be a talk on this Thursday morning. So I want to talk a little bit about how this was sped up on Summit. The primary computation of this code is an all-to-all comparison of vectors. It's used to find features, traits of an individual, for example, maybe susceptibility to a disease that would be influenced by multiple genetic elements. So there's a need to do an all-to-all comparison to see what combinations are actually causing certain effects. And that from this arises an all-to-all comparison. It's actually computationally similar to a DGEM, very much like a scale-pack or parallel BLAS operation. And this is very computationally intensive. because it has degems, but also it's very communication intensive because large matrices are being transferred. Now, parallel laws and Scale-Pack library can do this. It does not overlap the communication with the computation. The newer Slate project has this focus to try to do this. So this code is written in C++. It uses CUDA, cuBLAS, and modified calls to the Magma library, and uses heavy overlapping of not only transfers between CPU and GPU, but also communication of matrices with heavy pipelining, and also OpenMP threading for the CPU work, and this is also overlapped. So the only way to get high performance is by overlapping everything with the code. I wanted to describe one of the algorithms a little bit here to kind of show how it was accelerated. This one algorithm is the custom correlation coefficient. The input to this algorithm are vectors, each element of which has a pair of bits to encode the allele data from a genome of an individual. The basic algorithm here is to take these two vectors, and in this case, each has one element, to take all combinations and enumerate them of the 2 bits, and then tally the number of occurrences into a table here. And the original method used different, packed the bits into a 64-bit word and used various masking and bitwise operations, and used the population count intrinsic and CUDA on the GPU, which performs in hardware a population count that counts the number of bits in a word. The new method using the tensor core is kind of a reformulation of this bitwise method, and the way it works is each vector is now replaced by 2 vectors where the counts are taken of the number of 0 bits and the number of 1 bits in each entry of the original vector. And when you apply an HGEM to this huge matrix of vectors, computing V transpose V, you basically get all the 2x2 tables. And because you only have 2 bits that are needed in the input, it can be stored as FP16 data, and it has to be accumulated as a FP24, FP32, 32-bit arithmetic for accumulation, which runs very, very fast and uses the tensor cores on Summit. And here are the performance results here. So the speed is enabled not only by the tensor cores, but the near perfect scaling by the excellent InfiniBand network with adaptive routing. And the computation pattern is very much like the MPI graph benchmark, where you have the set of nodes and you're sending to pairwise sending to nodes of varying distances between the original node, and performing extremely well with very low congestion. We're getting equivalent to 86 teraflops per GPU of performance out of a theoretical peak of 125, and this is 4 times faster than the bitwise method.
So, I believe there's not much high precision required in this calculation.
Right.
And that's why you intend to use tensor cores.
Yes.
Is that right?
Yes.
Yeah, because I think 86.4 teraflops will you lose on precision a lot. Combining, bringing from FP32 to FP16.
Yes, and it's because of the very specific nature of the problem that the data is actually, there's a small number of bits, unlike a lot of modeling and simulation applications which have 64.
Is it for this application understood where, say, the adaptive routing helps, and also have you any idea of, had you a chance to quantify of how much adaptive routing helps you?
I can't quantify it. As soon as we had it available and enabled, started using it, didn't want to look back. Some of the, I don't know the exact numbers, but the earlier scaling to like 1,000 nodes was much worse. I can't quantify it, but you just think about each GPU has a matrix of about 1 gigabyte, almost a gigabyte of size, and all the GPUs are communicating at the same time. And so, I mean, you can see there's potential for lots of congestion. And the MPI graph results that Chris Zimmer did, it's in the paper actually. the ST18 paper, a very stark contrast between enabling and not enabling the adaptive routing. This is an interesting graph that Jim Rogers collected this data for one of the runs of Comet. This is a power usage of Summit. In the x-axis here are the time in seconds of the run. Now the actual run goes in phases. Each phase has this pipeline of communication and GPU usage. And there, in the actual runs in the graph, the performance on the last slide, there are actually 4 of these in the single run of Comet. And this is for one of those phases, and you can see here, you can actually see sort of the pipeline effects of actually sending data while you're computing, and then you have to stop computing, wait for the send receive to finish, and that sort of thing. So we're getting 11.45 megawatts, which Jim told me is actually higher than HPL, which is kind of interesting, and 206 gigaops per watt here. So very good usage of Summit. Some issues with using the tensor cores. One issue was that the actual problem has tall, skinny matrices. So someone at NVIDIA suggested that to get higher performance, we store it in have the axes transposed so that the shorter axes were closer together in memory, which was stride 1, and this roughly double performance. Another thing is HGEM performance is very dependent on matrix size. It's the same as DGEM. It's good to have a very large problem to solve, very large matrices to solve, as large as possible to basically amortize various overheads. And the same is true here, but it's not a continuous graph. It's actually scaling up the matrix size. Also, there's an issue of trying to get a power of 2 or a multiple of a small power of 2 for the matrix dimension. That improves performance. But if you pad too much, then you're kind of wasting. So there's some issues here of just ran a lot of experiments to see what would be best for this.
Is it due to the memory band conflicts or something?
It could be. I didn't really get an explanation. You know, the actual call to the gem actually requires some amount of padding up to I think a multiple.
I think it should not be the order of 2 because it's one of the.
Yeah, it appears to be something of that nature. But then they said, oh well, there's a requirement. You have to have a multiple of 8, but try something even larger, and that might give you better performance. So anyway, I didn't really get the hardware details about what it was. So another thing is the call to HGEM has a tuning parameter for the algorithm to use. And for CUDA 9.2, there were 16 different choices, and there's a default, and then you can tune it with these different choices. And just through experiment, it turned out this was the best. It was significantly better than the default. And we're hoping that they make improvements to the default for the call to this, so you could get high performance without having to worry about this setting. One final point here, kind of an interesting feature here is that there's a surprising data-dependent performance of the HGEM using the tensor cores, and we're kind of not used to this so much for the CPU. Basically, performance would be independent of the actual data. It might depend on the path, if there are conditionals in the code, the execution path. But if you just have no dependence on the execution path, you wouldn't expect to have different performance based on the data, but as it turns out, you get 113 teraflops if you operate on matrices full of zeros, but if you have random entries, it could drop as low as 95 teraflops. And there's kind of an interesting reason for this, that it has to do with power throttling. Here's basically for a test on one GPU. If you're computing on zeros versus computing on matrix of random numbers, it takes more power. It goes up to the 300 watt power cap of the GPU, and this forces the frequency to throttle down, and so you lose performance. So it was kind of a curious effect, kind of hard to figure out what was going on and track it down, but kind of interesting. I wanted to comment that we were thinking about other possibilities of using reduced precision. In the past, scientists have usually said we need double precision. Don't even go there in terms of trying to use reduced precision. We looked at in 2009. We started looking at we looked at the different car codes for Titan to see if we could use reduced precision. It turned out that one of them could, lamps, which got a good speed up from using mixed precision. But other codes, for example, S3D, there was a study where they actually tried single precision, and there's a graph that shows as you iterate forward in time with the explicit time stepping that you lose stability and you really can't use single precision. However, if you get a 16x performance improvement, it may cause you to look again at some of the algorithms. Jack D'Angara's group is actively working on this, and they have actually a talk at SC. They've got some great performance improvements with iterative refinement for solving dense linear systems. And as I mentioned, the deep learning people are using this. There's been work in the past to explore use of reduced precision in parts of certain algorithms while retaining the full accuracy for the final solution. So anyway, how am I doing on time here?
We're a little bit past time, but we started a little late. So how much more do you have?
About 4 slides, so I'll try to go through them quickly.
Thank you.
Okay, so just some comments here. I'll go through quickly. Most users are using basically one MPI rank uses one GPU and several CPU cores. This is natural for people coming from Titan because this is the kind of node we had on Titan. We have requested that we get JS run options to run arbitrary layouts of ranks, non-uniform resource sets on the node, which some applications will need and will provide more flexibility. We had initially long MPI init times. These have come down quite a bit as we've worked with the vendor on this, and it's gotten much better. And basically, because we asked for beta software, it is rough around the edges, and so we get the software, we report issues, and the team works hard to fix them. So actually, I think I just need to pretty much skip to the end here. It's about out of time. I'll just recap here that Summit is a very, very powerful system. Users are already using it effectively, and we're really excited about it. We've had issues that we worked through with the vendors, and things have gotten much better. And we're looking forward in next year to lots of science teams getting on to use the system. So, if you have any questions.